as Cindy mentioned, Yuwu Chen works at SDSC. He received his PhD from Louisiana State University in chemical engineering with an emphasis on molecular dynamics. So it's no surprise that he's found his way to a love of all things HPC. One of his key responsibilities is to provide a high degree of HPC support to the research communities across UCSD and other institutions. He's a Singularity user and has provided user support in that area since 2019. He's also become an expert in R, which is why he's talking about that today. His focus is on the TAC resource, and it impacts users and programs all across UCSD, and it's focused to the UCSD community. So if you're curious about the TAC system, you can reach out to them about getting onto it. He also enthusiastically supports all aspects of our HPC training program, which I really deeply appreciate. It includes maintaining, installing, updating relevant software, developing training materials, contributing to our training events, including our summer institutes, and presenting webinars such as today's webinar called R for HPC. I'm looking forward to this topic. So with that, I'll turn it over to you, Wu, and you can start sharing.
So hello again, everyone. So my name is Yu Chen. I'm from the San Diego Supercomputer Center. And today we are going to learn R for HPC. And we are going to see lots of command lines in today's webinar. And they are either R commands running in a R console or the Linux command running in a bash shell. So for those R commands, I put them in a blue box with a R logo like this. And those command lines begin with the greater sign because that's a unit for the R console. And for the Linux command, I put them in a gray box with the bash logo, and each command lines begin with the dollar sign, which is also unique for running Linux command. And here you may find some slides have a basic 101 logo like this. Those slides are for the background knowledge for R or HPC starters. So I will only do a quick review or even skip those slides in today's webinar because our time is limited. And if you are starters of R or HPC, you can just read those slides before or after this class. Now here's today's outline. So we have two parts to introduce. In the first part, I will introduce how to customize your R on HPC, which includes 3 sessions. We can learn how to inspect and configure your user environment with R commands and how to install R packages and view those R packages on HPC. And then we can learn how to install R from the source code. In the second part, we will get some base knowledge about the parallel computing in R, which includes the implicit parallelism and the explicit parallelism. And the last session is about how to import big data into R more efficiently. Okay, now let's first go to the user environment inspection inside R console. So you can run Linux command in R with system or system2 R functions. You need to use them to check the system status. For example, you check what a certain environment variables that R can get in a R session, or sometimes if you need to install a R package that requires to link some external applications, then you need to set up those libs or head files in that R sessions. That's why you need to run the system or system2 functions. So to run them, it's quite simple and straightforward. You just include the Linux command you want to run in those functions, and it will return the output. So here are some differences between the system and the system2 functions. So the system function can run the entire command in one string. So you don't have to divide your command and Linux command and arguments into different sessions. So which is I would like to command to recommend to run. For the system2 function, that it's more portable and it can run in Windows, but we don't have Windows in our HPC environment. So generally, I would suggest you use the system functions to run Linux command. If you want to assign the system function output into a R object, you may need to use additional argument in the system function. Otherwise, for example, in this example, we want to get the value of CPath, environment variable CPath, and then assign the output to an object, R object called A. So in this example, if we just run the system function, uh, we will get the output on the screen at once, right after running this command. And that string is not saved in the A, but the A is just a zero, and it's an integer object. But why? Because the default in the system function just print out the output and only return the exit status. Since we run this command function command successfully in R, so we will return zero for success. It cannot save the path to the R object. If we want to do it, we need to add the intern equals to true option into the system function, and to tell R not to print, but also just capture the output as the correct vector. So here is the proper way to assign the output to the object. If you just want to inspect environment variable, R has a built-in function called systgetInv that can help you to inspect the environment variable in R sessions. You can just check any environment variables you would like to know with that system_get_in function, or you can assign it to our object directly. That that won't cause any problems. Or if you want, you can use the system function to check the environment variable, but the system function cannot change the environment variable inside the R session. In this example, we want to add my home directory path to the C path, and then check whether it has been assigned. But it turns out we don't have the path in my home directory. But this is why, because the system and system2 are all running in a bash child shell, and the environment change in a child process never affect the parent process, which is in where your R session is. So to change the environment variable in R, we usually we use a function called system set in im. This function is very useful if you want to assign or change your environment variable in R, and you can just set the path like this example. You can paste the two strings of the path. The first string is my home directory path, and the second string is the system C path, and specify the separator is colon sign. Then the system get in function can show that the C path now has been changed, including my home directory path. So besides the functions, R also can be configured with the configuration files. We uh we're using the R environment or the R profile. Both of them can be placed under your home directory because they are hidden files. So if you just list in your home directory, you might not find them. But if you know how to find out the hidden file, you can open it or list it in your home directory and use them for your R configurations. They are getting executed or evaluated when the R starts, and they are useful because they are not on yeah they can just be applied to the R console and the RStudio. So if you are using RStudio, you can still using the R environment or R profile to configure your R. So the R environment is solely for setting the environment variables. For example, if you want to change the compiler or compiler flaggers comes with your R, and you want to modify how the R compile its packages, you can set those environment variables in the R environment file, or if you want to add libs header files of some external applications for the R package installation, you can also directly set those environment variables. So in this example, once we open the R environment in the in a text editor in Bash, then we can check what's the environment variables has been set, and if you want to add something new, you can just change there. But it's more common to use the R profile for such text configurations because R profile is for running specific R commands or scripts when the R starts. So it can be placed in your home directory, and when it's in your home directory, it has the highest priority to configure your R. Of course, it can also set up environment variables. You can in this example, you can set your LD library path with the system set env function, but you can just add that function into your R profile. So every time you start your R session, your LD library's path will be changed and updated to the one you would like to use. Okay, here we just finished some basic introductions about how to inspect and configure your server environment in the R. So it's like quite easy and straightforward. And I hope you use that session for the warming up because because the next sessions will be more and more complicated, and hope you will enjoy. Next session we will talk about how to install R packages on the HPC. Now here are some basic 101 commands you probably have known for a long time if you're using R. So you can run the library function to check all available packages you have in your R. And if you want to check the default library, you can add the option with like .library. And if you want to know the current loaded packages, you run the session info. And if you want to load a certain R packages, of course, you still use the library function. If you want to detach or unload a R package, just use the detach function. When you need to update or remove any R packages, you can run this update packages or remove packages command. Now let's go to something special on HPC. If you want to install R packages on HPC, you most likely do not have root privilege on HPC as a user. But still, you may want to install your R packages into a desired location. Sometimes it can be in your, for example, sometimes it can be in your home directory or sometimes in your project or scratch directory. When you find your home directory is almost full. As you may know, the R can search the library path that is using with the .lib path function. In this example, once I run that .lib path function, I get two output. Each output is a path of my R packages. The first path is the location in my home directory, and the second one is the location of a system-wide library location. The order of these locations matters. The first location is the one you can have your R packages installed, and once you load those packages, if you have R packages installed in both locations with the same name, then the R packages in the first location will be loaded at first. If you want to change your library path, you can still use the same .lib path function to set your desired locations. And of course, you can also add that function into your R profile. So once you add it and save it, every time your R session is running, R can uh, get the correct location you want. So here is a very common thing you will find when installing R packages. The R packages can be built either from source or binary. The R packages on HPC are generally compiled from the source if you run the install.packages function. And here are some examples. In the R console on HPC, once you run install.packages, you will notice from the output saying it's installing source package, and then you will find a few compiler command line output saying the R is trying to compile the packages. On the other hand, if you run the same R console on your Windows PC, most likely it will not be compiled from source unless you have configured your PC to use the GCC compiler or other compilers. On your PC, you are likely to see to find some messages saying installing binary packages. There are some other scenarios when installing R packages, like R packages installed with dev tools or bioconductors are generally from source because those tools are trying to compile the source code and build R packages. If you're running RStudio building a singularity container on HPC, then you're likely to get some R packages from the binary. And if you use conda to build R and R packages, most likely those R packages are just built just from a pre-built binaries, so they are binaries only. So why this matters? So let's do a quick comparison between the source and the binary R packages. If you install from source, well, the compilation takes time, and so the installation process is slow. Is that this is particularly true when you're building packages with multiple dependencies. But the good news is it has excellent link to the system libs, and most of the time it's proved to be working. Once you install it, when using it, you know what's going on, and you can use it very easily. On the other hand, if you install R packages from binary, it's very fast because all those binary are already pre-built. What's going on is the R just download those binary to your library location, and you can for you to use, but they may or may not link correctly to your HPC system. They may run slow or even cannot be loaded because they are not be complied on your HPC cluster. So sometimes they may not just work for you. If you want to force R to build R packages from source, when running install packages functions, you can add those two options to your .R profile or before running every time running the install packages, so that once the options are accepted by R, the installed packages can always build from source. Okay, so if you want to test your R package installation, a good choice for testing R pack that one is the package config, or sometimes I use the phrase package, and once load that phrase libraries, every time I run that function, it will phrase me. So that's two packages I would like to recommend for you to test your R package installation on HPC, just to make sure every installation process can work. Okay, so next we were going to talk about the install your own R from source on the HPC system. So why do you need to build your own R from source? Because on a HPC cluster, you cannot easily have a nearest system-wide R because R released those minor versions very quick. Like every few months, it has a newer version, minor version. So on most of the HPC clusters, you cannot get the newest one. Or if sometimes you want to keep using the same from the same version of R, maybe you use for years for your research, and you want to keep the version the same so you can better configure your R packages and maybe get the same performance, and you want a desired R version to share with your colleagues so so to make sure you're all on the same page. That's that's the thing usually you cannot get on the HPC cluster. Or maybe you can ask HPC staff for help. Maybe you can ask me for help, but can they really help with the text list about? Um, Unfortunately, many HPC user services staff are not R experts, so they may build a R version that works for you, that appear to work for you, and you get that version and you run it and it appears to work, and both of you are very happy. But can it really run as fast as you would expect on HPC? We don't know yet, so that's why maybe you can learn something from today's webinar to know how to properly build your R. And I know some users just choose to build their R with conda. So using conda to install R and R packages is very convenient. Of course, it's fast, and you get a isolated conda environment. You just need to learn some basic conda and member knowledge to know how to build things with conda. But there are some disadvantages, like the R or R packages are not the same as the clean official ones. They may use the different compile flags, different blast or lab pack. Some packages require external system libs, headers, or compilers. And also in a conda environment, the dependencies are locked. So updating R packages may updating many other R packages you don't want to change. And usually those R packages are from different conda channels. Like they can be from conda forge, bio conda channel, or R channel, causing some solver conflict leaks. So if your conda environment is too complicated, the conda solver might not be able to satisfy all requirements. And also some RStudio features may be limited when using conda star. That one caused some lots of troubles to me when I was trying to troubleshooting some R users problems earlier this year. So that's why I listed here. Now, if you want to install R from the source main, that we will learn those stuff from scratch. We use the R 4.5.2, which was just released like 1 month ago as an example. As usual, the CRAN uh, has a very long uh, user manual to tell how you'd like how you should or how you can build your R from source. That list is always very long, but fortunately we don't really need to read all of them, and that's why you're attending today's webinar. And we need meet three requirements: the compression libraries, which are required by R, and we also need to build the glue readline for the command editor history and autocomplete. This is for your convenience in the R console. And we also need to build the blast and LAPACK from some libraries on HPC. It's usually from the Intel Max Kernel Library (MKL). That's for better parallel computing. Here, the next few slides will give an example on SDSC's expense. Now we just need to load a few modules like the compilers, the Intel MKL, and the CPU software stack. But there's no need to load or install any compression libraries because on Expanse, those libraries are already available. But what if they are not available? Those compression libraries are not available. You can just search the modules on your cluster to see if you can find any one of them. If you can, just load those modules. If there's no module available, you can just build them, which are quite easy. You just download source code on tar and configure and compile into one place. So for your convenience, and once all those compression libraries are available, you can keep building your R. Installing the glue readline is also straightforward. That readline is for the command added history on the auto completion in R, and once you get it enabled and built, it's running R commands in the R console will be easy. And again, the process is straightforward. You just download source code on tar and configure it to install to your home directory, and you just need to specify the passes to the anchors, and then build it. Once you build it, you don't need to add the passes to your environment variable path. You can just specify the path to your readline when building R. Okay, so next, Blast and the LAPACK build it's the key we need to understand today. So Intel MKL is a common source to provide external BLAS and LAPACK on HPC. Those two libraries will impact the parallel computing performance of R on the HPC. If we want to build libraries against MKL, we can either link R against a single shared library, which is called libmkl, or we can explicitly hard-coding which interface and threading model to use when linking against MKL. We can choose the single-threaded MKL or a threaded MKL with the glued OpenMP, or if you have an Intel compiler, the Intel OpenMP. When using the MKL libmkl, it just loads the appropriate backend at runtime based on the environment variables. The R building process is easy, but it's also flexible at runtime. So that means at runtime, at R runtime, you just need to set up the MKL interface and 13 layers, like the examples below. Once you give give the values to those two environment variables to set up the layers, then your R will get those values and can run some functions in parallel properly. So here's how to link R against the single MKL library, you can just specify the path to that MKL library and also specify the with lab pack library. So when BLAS is configured with this way, you can just add in the with lab pack. That means also compile the lab pack in the same way later. If you want to hard code the interface and the threading models, you can do that by either sequencer MKL or the multi-threaded MKL. This hard coding gives full control and works on all systems, but it's just fixed at runtime. If you are using the sequential MKL, that means all operations will be executed on one CPU core. So there were no internal parallelism, but this is good to avoid any oversubscriptions because the parallelism is not just does not just exist in the BLAS and the LabPack, but it can exist at a higher level, like some functions we'll learn later. If both parallelisms exist, then you will get oversubscriptions and your R code may run slower. So if you just build the MKL in a single threaded, this can avoid that problem. But on the other hand, if you want to build MKL with multi-threaded using the GCC OpenMP, that's good too. That means some functions you will use in R can run across multiple CPU cores automatically once they run those functions. And you will also can have a full control of how many threads you use before starting R. So here is a practical recommendation for R, whether to use the sequential MKL or the multi-threaded MKL. If your tasks in R are mainly about running parallel R jobs with those parallel functions like the for each, make apply, some functions like that, then probably you can consider build R with the sequential MKL to avoid oversubscription. If you are doing large linear algebra with those like a linear regression functions or PCA functions very frequently in the R session. Maybe you need to build a multi-threaded R because those functions can be run in parallel automatically once you build R. And here are the two config lines to build the sequential MKL supported R and the threaded MKL supported R. What you need to do is you specify the path to your MKL and specify a few system libraries, and you don't need to worry about whether those libraries what do those libraries means because they are specified and already provided in the official CRAN menu. So you can just follow the menu or follow this commands I provide here to build your R link to either sequential MKL or threaded MKL. Okay, let's take a quick review about three ways to build BLAS and LAPACK from the Intel MKL. You can choose either from building uh, building BLAS and the LAPACK with a lib MKL, a single MKL library, or a sequential MKL library or multi-threaded libraries. The first one is simple setup and flexible at runtime, but you need to specify the environment variables to use before starting your R. For the last two, the sequential MKL and the multi-threaded MKL, they are fixed and hard-coded when you build your R, and you don't you don't need to specify any special environment variables, but just run R as usual. And here is a general steps of installing software from source. You download them, and then unzip the source code and compile with config, make check maybe, and make install. And once it's done, you just add the parts to the system with uh those those environment variables. Now to install R on HPC, you download and unzip the source code from Crane and then compile from source. The first two stop is first step is download and unzip and change the source code directory name, and then you run one of the config commands and then compile and until you get the executables. Then you add the path to your executable to the path environment variable. Okay, now with your own R, you can easily get the newest R, and you can choose certain R version you need. And you can, of course, build a R in a commonly shared location, like your project directory with your colleagues, and share that R and its libraries with your colleagues, and you can be the manager of your R. Okay, that's the first part we have talked about how to customize your R on HPC. I hope you enjoyed the talk so far, and let me know if you have any questions. If not, then in the second part, I will introduce the parallel computing in R. So what are the benefits of parallel computing? You can get your result faster with parallel computing, and you can solve a large problem with parallel computing. And here is how to judge whether you need to parallelize your code in R when running on HPC. If your code is running slow and it can be parallelized, and you found it's not yet to be parallelized, then you can consider parallelizing your code. When running those parallel computing in R on HPC, you will find that the performance will be much better than running on your PC. If you have a software uh, that can run in parallel, like the R. R is a software that has many parallel functions, and you have a hardware that can run parallel computing, like multiple PC server or workstation. Then you can make sure that the parallel computing is possible. So in R, we use the system time function to evaluate how much time a function may take to confirm running code in parallel is indeed faster than running in serial. And also you can use this uh, function to find out which line of your code runs slow, because this function, system time function, can be used to time every function in your R script. Like in this example, the the system time function is measuring the time of generating a large matrix, and it turns out this matrix function runs for almost 10 seconds, and you can just look at the last number in the output. That is the war time of the function running in second. And on HPC, it's very common to see that for a fixed size problem, adding more workers, usually like adding more CPU cores or threads or process to solve the problem, may not reduce the time linearly. For example, moving 200 boxes by 200 people versus 1,000 people. If moving 200 boxes by 200 people to certain distance takes 5 hours, but moving 200 boxes by 1,000 people to the same distance may still take like 2.5 hours rather than 1 hour, 5 times faster. So that makes us to measure how the performance is good or not in terms of efficiency. So efficiency is the key measurements of parallel computing. We still use the same box moving as the example. If moving 200 boxes by 200 people takes 5 hours, and if use by 1,000 people, it takes 1 hour. Then we have 5 times more people, and the speed up is 5 times. Then the efficiency is 100%. That's it. That is pretty good. That's ideal. But in reality, it's very hard to reach that efficiency of 100%. Most likely, like in the next example, we hired 5 times more people to move the boxes, but the speed up is just 2 times. Then the efficiency is just 40%. And the efficiency usually will reduce in some parallel computing when more workers join, indicating many workers are idle or waiting for something to run. Okay, now if we build our R in the multi-threading, then the R can run many functions in parallel implicitly. Most likely, those linear algebra and the related calculations. For example, the matrix multiplications, the linear regressions, decompositions of a matrix, and the inverse matrix, and the principal component analysis. Those functions can be run in parallel implicitly once you have a multi-threading R. So you don't need to parallelize your code, to run them in parallel. So for So for the R we built introduced before, if it is linked against that MKL library, libmkl, then before running R, you just set the interface and threading layers to tell R which interface and which threading you are going to use. The threading specified here is for using the glue OpenMP. So once the R started, it knows that it has the multi-threading functions. Or if you build R with a multi-threaded MKL at the build time, the GCC interface layer and the GCC OpenMP threading layer were already hard-coded, so you don't need to do anything to use the multi-threading at the runtime.
Yuwu, we have a question in the chat.
Oh, yes, go ahead.
How can I know if my code or specific functions I use in my code will run implicitly in parallel or not?
Okay, that's a good question. First, those functions running in parallel implicitly are usually about related to the linear algebra of calculations, like the ones I'm listing here. If your function is on top of those linear algebra functions, then it's very likely that your function is already run in parallel implicitly. And also, if you are not sure, then the next slides we are going to talk is about how to know if a function has a running in parallel or not. So, like in this example, we are running a matrix multiplication with one thread. So before starting R, we just tell our our cluster or the node we are running jobs to use one thread, and then inside the R session, we are doing a matrix multiplication and the time how long it will take. And in this example, it takes 177 seconds, and and uh, when when the calculation is still running, the R is still running, the calculation, we can open another terminal and run top command in the bash shell on the same node, and then we'll find our R process and the CPU usage in percentage is close to 100. That means we are running one thread on that with that R process. Okay, so if you are using eight threads for the same matrix multiplication, the result shows that it took a much shorter time, and it only took 31 seconds. And also you can notice that the elapsed time and the user time are very different. That huge discrepancy between the user and the elapsed time is an indication of implicit parallelism. So this also applies for the R function you want to test. If you found if you are using multiple multi-threading and you found the elapsed time and the user time are very different, then it's likely that your function can be run is already run in parallel. And when it's still running, if you check the top the process in the top command, you will say that the CPU percentage is close to 800. That means that our process is running with multi-threading with likely with eight threads. That's to confirm that it's running in parallel. But how about the efficiency? Now we have run the code in parallel. the efficiency in this example is around 70%, which is not bad. Okay, that's about the implicit parallelism. Next, maybe we need more parallelism, and we have to consider more write our own code or parallelize something. Now that's called explicit parallelism. So next session will be about that. So in R, a classical package for the parallel computing is called parallel. The parallel package provides the support for parallel computing in R. This is a very classic one since R214 in 2011. This parallel package can spawn multiple processes as workers to run independent tasks. Once we have that parallel package available, we can choose one of the explicit code methods to parallelize our code. For the first one is running the for each do par loop, which is a parallel version of for loop, or we can use the make apply function. Both are parallel at a high level, so be cautious to see them together with multi-threaded functions we saw before to avoid any oversubscription. Okay, so the for each loop is nothing but just a very special for loop in R. You can install a do parallel package on top of which is on top of parallel iterator and for each, and then you will get the for each running in your R sessions. You can then specify how many workers to use in a cluster with the make cluster function from the do parallel, and then you can register the workers clusters with the register do parallel function, and then you run your for each do parallel session. Once you're done, you can just stop that cluster with the stop cluster functions. And here below is the do parallel example. You can load the library. Register. You can then create an object with the make cluster and register it, and then you run your for each and stop clusters. Okay, so how to create workers on a single node? You can just give how many number of workers you want to use into the make with the make cluster function, and if you want to run this arco for each loop on multiple nodes, then you will need to give a list of the host names into the make cluster functions. So if your cluster is running with Slurm, here is the code to control show host names Slurm drop node list to get the list of the host names and then assign it to the make clusters. Once the workers are created and registered, you will find those work processes available in the top output. Like for this, for example, we just ask to create 8 workers, and you will find 8 R processes ready in the background for running parallel code. Now, the key part is the for each packages run similarly to the regular for loop, but it can run in parallel with the operator do par. The syntax is very similar to the for loop, but it's just a little bit different. You can specify your statement inside the for each and run it in parallel. And this example shows how to run the square root of 1, 2, 3 repeatedly, and then save the result into a vector. And once it's done, the result will be saved into a vector A, which is a numerical vector. So the syntax is easy and easy to understand. But how about we're doing some real case study, which is about running 10,000 bootstrap iterations for a binomial logistic regression. So this example is from the do parallels menu, which is commonly used for teaching the do parallel. If we are running 10,000 bootstrap iterations with a regular for loop, I'm listing the code I have here. And you can see that if we run with the regular for loop, it takes 12 seconds to finish. If we are using the code from them, you can see that it only takes 2.2 seconds to finish, and it's a code very similar to the regular for loop, and you don't have to worry about any special rules or problems. And if we calculate the efficiency with 16 words is around 33%, which is still good in my opinion. But you know that you are using 16 cores rather than running the for loop with a single core. Of course, we can nest the for each loop. We just add the nesting operator outside of the do par, and the nesting operator is useful if you have large tasks and at least one of the loops may have a small number of iterations. But in many cases, it's safer to only parallelize the outer loop. So we can just parallelize the outer loop with the for each do par and still use the regular for loop inside the nested loop. And here is the same case study running bootstrapping 10,000 times, but instead of sending 10,000 tasks to those 16 workers, we just create a large chunks of 16, and then we use a nest for loop and to just only parallelize the outer loop, and inside the loop is still a for loop, and you can see that to run the same iteration, it only took 1.3 seconds to finish. Now the efficiency is 55%. Next, we are talking about the apply functions in parallel. You may already know that R has many apply functions. The regular apply function evaluates a function over the margins of an array. And this is very unique in R. There are multiple apply functions like L apply, S apply, T apply, and M apply. But the one that can run in parallel is called max apply. The apply is in the apply functions for the explicit parallel computing. The syntax is still similar to other apply functions. You just give the objects and a function to be applied, and you can specify the number of calls to use, so the Mac apply can run in parallel. Once it's done, it will return a list of the same length as x, and each element of which is the result of applying that function to the corresponding element of x. But the one short is the Mac apply can only run in a single node. Okay, still we're going to the same case study running 10,000 bootstrapping iterations for that logistic regression. Now here is the code. We use the Mac apply, and we specify how many iterations we have, and we just insert that function, bootstrapping functions into the Mac apply, and then we specify the code we are using, and it only took 0.9 seconds to finish. That's running faster than the for each, right? And the efficiency now is close to 80%. Okay, so now which function to choose? The Mac apply or for each do par? If your code is only running on a single HPC node, then go to the Mac apply. If you need multiple HPC nodes, then you have to use for each do par. And your data set is very large, then Mac apply can give you better performance. But if your code has anything to do with the CUDA GPU or any large C or C++ libraries, then Mac applies fault may conflict with those external libraries. So you need to choose for each. And the last, for generally speaking, if your tasks are small and easy, you should choose the Mac apply functions to parallelize your code. And it's common to know how many workers to use once we know how to parallelize our R code. Is this good? The more the better? Usually not. Because for fixed size problems, adding more workers to solve the problem may not reduce the time linearly, and you may need some try and error in a scaling test to determine the best workers to use, or the best computational resources you want to use. Now back to our case study, running 10,000 bootstrapping iterations. We know that using 16 workers, the bootstrapping can finish in 2.2 seconds. How about we change our CPU cores from 1 to 4, 8, 16, 32, and 64, and then measure the work clock time. And if you get the clock time and the draw a chart, you will get how many you will get a picture like this, and the green line is the real time that it will take, and you will suddenly find the fastest run, which is using 16 cores in 2.2 seconds. But do you really need 16 cores? It depends. It depends on how much computational resources you want to use, because on the HPC running, your job are will be charged by by service unit, which usually are not free or at least not limited. Your resources are not limited. So if you then look at the efficiency of each case by varying the workers, you will see that maybe the efficiency is reduced a lot when you go from 8 to 16. Sometimes maybe you just want to choose to use less workers for higher efficiency. Okay, the last part is the big data import. And as an R user, you already um, you already know that how to import data, raw data into your R sessions with the read.csv and read.table. But when importing some large raw data at the gigabyte level or even large one, the regular read.csv or read.table may take a long time to load your data into the R. Here, you can consider the fread function from the data.table packages. That's very simple, and it's the single most widely used read.csv but faster replacement. And it's easy to install. No other R packages required to be installed, and it's easy to use. Still one command line to import R data, and the syntax is similar to read.csa and read.table. And once you use it, it automatically runs in parallel with multi-threading. And it also offers many other options to make it run faster. For example, only load part of the the data, and it remains actively maintained. So that means you don't need to worry about it's already out of date, and some people are maintaining these packages, and it's very useful. But it has a limit. Assume the entire dataset is loaded into your node's memory. Expands 256 gigabyte node can load a dataset of like 100 gigabyte if all memories are allocated and the entire dataset set is loaded, because you need more memory to do some calculations or data processing later once you import that large data set. That means if you have a even larger data set greater than 100 gigabyte and to use the same expense node, you can use you should choose other R packages to handle the data, like the one I listed here, the Arrow or DB. Those packages are more complicated than the data table package, but they can well handle much larger data sets. And for this fread example, we choose to download a dataset from UCI's machine learning repo, which is around 200 megabyte. We just download it with the widget function. And if we want to import the raw data into the R session with read.csa, it will take 30 minutes, 30 seconds. If we use the fread function, you see the command is still just one line and the syntax almost the same. It's only 2.4 seconds. If we already know the column name and the data type of each column, like this example, we already know the name and the data type, we can make fread run even much faster. we just specify the column name and the column data type and use it in the fread, and the data reading just to 0.26 seconds to finish. Okay, so if we have an even larger data set, then the data set might not be saved in the in a CSV format or the text format anymore. The modern large data set to be processed in R is usually in the Parquet format. Parquet files don't explode memories like CSV, and it's easy to scale or compress. And both Arrow and DB packages can partially load the Parquet file, and that gives a bigger advantage of using those packages to load large dataset, because even the dataset size is multi times larger than the available RAM on your node, you can still load that dataset. Now, this dataset example has 37 gigabyte, which is actually not big enough, but it is enough to demonstrate the Arrow at DB. If we import that dataset with the Arrow, it took around 15 seconds, and the same for the DB function. If we just need the metadata scan with the DB, it can take even faster, just 0.2 seconds. Okay, here are the take-home messages for today's webinar. We first learned how to inspect and set your environment variables in your R sessions with the system function, system get in, and the system set in functions. And we learned there's a configuration file to run some specific R commands or scripts when starting your R. And if you want to get reliable and fast R packages, you need to make sure to compile those R packages from source. If you need to get get the newest or the desired R, you should build your own, and you can specify how to build your R, BLAS, and LAPACK packages for parallel computing. On HPC, it's mostly linked against the Intel MKL. And when multi-threading is enabled, the implicit parallelism exists in many R linear algebra functions, or the functions on top of those linear algebra functions. If you want to parallelize your code, please consider use the for each do par and make apply. And we also learned the difference between those and under what situation you can use those functions. And the last today we learned how to import large data set with every narrow and dark DB based on the required memory, because for the large data set import, the memory is the key you need to consider. Okay, what's not covered is the data pre-processing in R on HPC. We don't cover that, and we also don't cover the statistical analysis part about R, and we're not talking about the GPU usage in R on the HPC, but there are some webinars available on at SDSC or online, and if you are interested, you can take a look. And if you are R starter, here are some resources to learn how to run R. And of course, you can get a bunch of tutorials and courses online and bloggers, and you can even run some R packages to help you learn R inside the R. Okay, so that's all I have today. Any questions?